So I just recorded this and forgot to save it. So let's do this again. So I'm currently working on this open source project OpenEcho, which is an open source project about building open source sonar hardware and software to drive all kinds of ultrasonic transducers between 40 and 1000 kilohertz. So this allows you to use this shield, and you stack it on an Arduino Uno or Arduino, any Arduino Uno R3 or R4 or even R2 probably. And then you can connect all kinds of ultrasonic transducers. For example, this could be one of these transducers. This is a 1000 kilohertz transducer meant to be used in water. These come from flow sensors, and these are very cheap, so €2.50 or something. But you could also use one of these sensors, which are 40 kilohertz transducers that are usually used in car parking sensors. Or you could also use marine grade transducers. I currently don't have one here, but you can pretty much use any transducer that is PZT based, PZT, like lead zirconate, titanate based transducers, which is basically everything you can find in old boats or in like even modern boats. But you can also use like old transducers you find on Facebook Marketplace, eBay Kleinanzeigen, or most boats do have them already installed. So you can attach like this new hardware to the old transducers and make them usable again. So you don't necessarily need to buy or use this the display and the electronics that is usually meant to be used for these transducers, but you can use all kinds of old transducers and connect my hardware to it and then reuse them again and get data out of there. It's like these transducers usually send out a beam shape that looks like a flashlight. So you're sending out, for example, a 10-degree wide beam, and everything in this beam gets reflected, and you can see echoes coming from there. If you want to see other stuff, you can use side scan transducers. These look like this, and they basically have, in this case, 3 transducers inside them, one pointing to the bottom, one pointing to the left, and one pointing to the right. And they all send out a beam that looks like a fan, basically. So it can be like 1 or 2 degrees in one direction, like usually to the side, and 90 degrees in the other direction. And one of these 3D beams goes to the left side, 90 degrees. The other goes 90 degrees to the side, to the right side. And the other one goes to the bottom. And by having a fan shape, you can see, or you can locate different stuff on the sea floor, for example. If you're searching for fish or using for sunken boats or something, you're usually using side scan sonars because you're basically seeing shadows on the sea floor, which is very cool. But you can also use these kinds of transducers with this OpenEcho hardware. This whole project started about 1 year ago, a little bit more than 1 year ago, when I needed a fishfinder or an echo sounder with a data output. And then I started to hack together this lucky fishfinder thing, which is a commercial €50 or €60 fishfinder you can buy from AliExpress or wherever. And I hacked it using an Arduino Uno and got the data from there directly into my Arduino Uno, and I could show like the raw echo column basically, which was cool. But this didn't scale, and I was also interested in building or having control over the whole hardware process and also the whole software. With the Lucky Fishfinder, I was also stuck to the frequency and also to the whole hardware as well, and also to the update frequency. So having my own hardware now lets me control all of these parameters by software, which is very cool. Then in January 2025, I built the first hardware with an Arduino with the TOS 4470 that can be stacked on top of Arduino boards. And by having this hardware, I was able to connect all kinds of transducers that are in between 40 kilohertz and 1000 kilohertz. So as I said, 40 kilohertz car parking sensor, but also 1000 kilohertz liquid or water flow sensor that is usually used in heating systems to measure the amount of heat that has been used in water heating systems. Yeah, this is I first started by buying 5 boards to test my hardware. Then I built a second version with a few improvements where I redid a little bit of the layout and added a voltage input selector and everything. And then I distributed them around in the community. And we are now at around 50 boards in the hands of makers all around the world, about 15 countries. which is very cool because people are using this for all kinds of projects. Some are just using this to refit their boats, basically, to not knock another hole in the boat where you put another transducer in, but to reuse the old transducers that are already in the boats, also to save money, of course. And if you want to have more data than just the DBT value or the depth below transducer value, for example, if you want to see the whole echo column, you have no way around getting like this, basically, because there's basically no hardware around that allows you to do this with all kinds of transducers. Usually you have to buy like these very, very expensive devices, usually meant to be used for research stuff. And most sailors or most hobby people don't really want to afford like a few €1,000 for an echo sounder. As I said, I needed this board for my own mapping project, and I haven't really done a mapping project since then, but the hardware is definitely capable of doing so. So what you basically have is this Arduino shield. You connect a USB cable to it, to your computer, and then you upload the Arduino firmware that is provided in the GitHub repository that looks like this. Then you enter two numbers that are like, first is the frequency in hertz, which is 40,000 hertz for this car parking sensor I have here, and a filtering frequency. So this is a register that has to be written on the TUS 4470 to do internal filtering in the chip. And you also have to set two jumpers for two different capacitor values, also for filtering. On the board, they are pre-selected for the 40 kilohertz, 200 kilohertz, and by combining the another jumper with the 200 kilohertz, you get a 150 kilohertz, and by using like only the custom value, you can use 600 kilohertz. So for the most used transducers, the board already provides you with the needed capacitor values. If you have something very special, for example, the 1000 kilohertz transducer, you can either just ignore this because the signal doesn't get much worse. But you can also desolder one of these capacitors and solder your own in. This is basically just for filtering, but it's not super critical, so you can basically ignore that for most cases. Yeah, then you just upload this to your Arduino. In this case, my Arduino is already flashed with this firmware, and then you can connect the Python interface with this. The Python interface is a PyQt-based software that connects via UART or via USB to the board and shows all the echo data that is collected. It updates on the right, so on the right there's like the latest data, and on the left you can see on the rest, scrolling to the left, you can see all the historical data. And if I take my transducer and point it to the ceiling, you can see there's a echo coming back here. This is all like the ring down time of the transducer. So if I put my finger on it, it becomes smaller. So if I put this in water, the ring down time is also a little bit smaller. But the most important thing is, like, after the ring down time, you can see basically all echoes from objects. So if I move this up and down, you can see the echo is also coming back faster or later. You can also see some scatter or reflections internal, like maybe in the ceiling. I don't know where these reflections exactly come from. Maybe even from the second reflection. I'm not sure about that. I can also point this to the wall on the other side. This is a little bit more backscatter from, for example, the lamp or something. Maybe this direction. There's lots of noise and backscatter. Also in this direction to the camera. I'm not sure if you can hear it. Maybe. And you can even see two reflections. One is from the camera and one is from the wall behind the camera. And yes, you can buy ultrasonic chips or ultrasonic boards for just a few bucks. For example, this one is like 20 euros or something. This one is 2 euros or something. This is also where I got the 40 kilohertz transducer from. These are very cheap, but for this one is I think it's a 20 kilohertz transducer type. This one has a digital data output, also very cool. This one is a very, very old one. I don't know where I got this from. But the downside with all of these boards and transducers is that you are stuck with basically the interpreted value. So you're not getting back a analog or a whole chart basically, or a whole list of reflection intensities like here. So red is strong intensity and blue is low intensity, but you're getting basically just the interpreted value of a strong target or a strong echo basically. So this doesn't allow you to see anything like in between these things. You're only getting basically a number that is like from here to 2 meters to the wall, and that's it. You don't really get like any scale between that. So it's just a black and white thing where you just basically just get the number of the distance of an object where the sensor thinks this should be the object. So if you're trying to see soft stuff, or if you're trying to see other stuff, multiple things on one picture or in one echo column, you won't be seeing these. Yes, this project actually, as I said, started for a mapping project of a lake. So this was mostly intended to be used for underwater transducers. These also work, like these 40 kilohertz transducers also work underwater, but they are not like designed to be submerged really. So yeah, they do work underwater, but it's not recommended to use them in water. You can also use this board to drive underwater transducers that are already embedded in a hull of a boat, for example. And I did this a few weeks ago when I was in the Baltic Sea, testing this board. And I used this 150 kilohertz transducer that is already part of the boat. And I just deconnected the wire from the depth finder, from the NASA Duo, I don't know, this device where the transducer was plugged into, and I just connected my own board and could drive and read the transducer from there. And the cool thing about this board is also like usually these transducers require a quite high voltage. The Arduinos run on 5 volts. But these transducers usually on the boats run at 200 volts. But the TUSS 4470 is limited to about 35, maybe 40 volts. So not like very high voltage. But this is actually, for most use cases, enough. For example, I got 50 meters in the Baltic Sea to the bottom and back, like so basically 100 meters covered. This picture is from 38 meters. I didn't have like a picture or a screenshot from the 50 meters. But you're already seeing that the echo is like a little weaker than it was when the echo comes back like from like only 20 meters or 19 meters or something. To get like the higher voltage out of these transducers, higher than 5 volts, I added a boost converter that I can show here. The boost converter that transforms the 5 volt from USB to 22 volts about. And this is all run at 22 volts or 25 volts about to basically increase the acoustic power from the transducer to see more echoes coming back. So this boost converter basically lets you boost the voltage a little bit so you don't need to use the 5 volts or use an external power supply. Because on this board you can supply power via this XT30 connector, but also via this V-in connector, which is the barrel jack on the Arduino. So you basically just need the USB connector, the board, and the transducer to get like these images. Yeah, as I said, the record was 50 meters. This is 38 meters in the Baltic, sand floor in the Baltic Sea in Denmark. This is about 20 meters, 19 meters, I don't know. And I see a lot of fish, like here, all these arches are fish basically, and the picture is flipped, so basically bottom is top and top is bottom, so the echo signal is sent or started at the bottom and then sent up and then reflects from the ceiling, from the seafloor, and then comes back, and this is basically the time it takes. In this chart this is already flipped, so top is top and bottom is bottom. I later flipped this in the software. Yeah, this is in the Kiel channel, so you can see like how the channel floor is basically changing over time. This is about 150 meters, like the whole from left to right. Depends on the speed you are running, but this is about 150 meters at 3 to 5 knots probably. Yeah, you can also see like different structures here. For example, this is like a very straight line, but also like this could be a hill. This could also be on the corner of the transducer, so on the beam shape. Not sure about that. This could also be like in the sand itself. So sometimes you can see a little bit into the sand. As you can see here, like there's a very sharp edge basically. But this is like all noise, probably from inside the sediment. Not sure about that. So yeah. This is a picture from the Schlei, which is in the northern part of Germany, connected to the Baltic Sea. and you can see like this is very shallow, like 2 meters or something, and you can also see like seagrass, these piles here basically, these red piles of something, and maybe this could be a stick or something poking up like in the water or whatever this could be down there. It would be very funny to dive there and like get it out of the water to see what it is. You can also see like multi-reflections, like there's a first reflection at 2 meters, then a second at 4, then a third at about 8 or 9 meters, then again at 12 meters and so on. And where the big piles of seagrass are, you can even see like where the sound energy is basically absorbed into the seagrass, and you can't see multi-reflections anymore at these places, which is very cool, I think, because you could even use this to basically tell something about the reflectivity or absorption capacity of some material inside the water. You could also read this from the intensity, of course. There's another picture at 6 meters. If you fish and something, not too interesting. Some stuff on the seafloor. This one is cool. This is called Stoller Grund, which is in the north of Kiel, where we have very shallow water, like 5 or 6 meters, and then it goes down like very fast. So as I said, like this is 150 meters, and this is going down to like 13. In the end, it goes down to 30 meters. Also a little bit of fish here. This is some noise, probably I touched the transducer or something. So this is all very sensitive to electrical noise. And so if, for example, we have a chart plotter on the boat, and if you switch on the old chart plotter, it basically emits a lot of noise into the electrical system, and then you see a lot of noise on the chart. So I turned this off while I took these measurements. Same with the radio. If you're switching on the radio, you see a lot of noise. Also, if I touch my laptop's trackpad, the noise also increases a lot, which is probably you can say solve that later with some smart filtering, but currently it's not too much of a problem if it's all like isolated and if you don't touch it. This is also interesting. This is in the Baltic Sea as well, like in the east from the Schlei, basically left off Sperrgebiet Schönhagen. There are a lot of rocks basically on the seafloor. Everything else is sand, and then there are a few rocks, and these rocks are all marked in the Baltic in the maps or in the charts. And we drove the boat there and tried to find these rocks, and a few of them we could actually find. So this, for example, is clearly a rock going up to like from 5 meter 50 or something, 530 or something. Going up to about 4 meters, which is actually quite a large rock. Would be funny to go dive there and see if we can spot that rock, which should be like a very large piece of stone. Also a second reflection here, even a second reflection from the stone, which is very interesting. And yes, that's basically my my vacation, like going out testing hardware.
Steinesucher auf der Ostsee. Bis nach links noch, ganz kleinen Tick nach links. Sorry. Ja, das glaube ich dir. Ja. Ein bisschen nach rechts. Ja, reicht schon, passt. Ganz kleinen Tick noch. Genau, ja, so ist perfekt. Du triffst ihn. Gut, wenn es gleich knallt, das wäre so dumm. Ah, da kommt er. Und? 3, 2, 1 und? Wo ist er? Was? Wo ist er? Wer ist er denn? Weiß es nicht. Okay. Ja, wir haben ihn getroffen! Ja. Den hast du sehr mittig getroffen. Wir haben ihn gefunden. Wir haben einen Stein gefunden. Da ist er.
Yeah, let me check. Yes, as I said, I started with this lucky fishfinder hack, then built the hardware in January 2025, then distributed a few boards to people of the community. The community is actually a large Discord group, mostly like people working on electronics, Arduino stuff, and people who are interested in ultrasonic stuff. So we're around 300 people right now. Lots of them have the hardware on their desk, testing them on boats, using that to build software and building a system to detect seagrass, for example. Another guy is building an MRI type machine with ultrasound, which is very cool. Another one is building a device to detect ice thickness. So they're using like 1000 kilohertz or something to detect the thickness of the ice. And the sound speed in ice is different from the sound speed in water, so you can basically see the sound speed shift or the sound speed change, where the ice is basically where the ice turns into water. So this is also very interesting. A few other people build like ROVs from there. We have a group building an ROV to map an old dock, an old lock here in Germany, not too far from here, which is very cool. Some people like building ROVs, underwater stuff. Currently the hardware looks like this. This is the Arduino shield. You can also add, like, as I said, the MT3608 boost converter to generate the higher drive voltages. But the base is this Arduino shield with the TUSS4470. You can either order this from JSC PCB using the hardware files. So in the GitHub repository, everything you need is provided. So assembly files and Gerber files for the production. But if you don't want to buy a whole batch of 5, you can also buy them from me. I sell them for 50 a piece right now. And you can email me via openechoes@gmail.com or via the Discord community server, where you can write me a DM if you like. I sent them internationally, and I sent some to India, to lots of countries in EU, some to the US, whatever you like. You can buy them from me, or you can buy them from JSC PCB directly. I tested these boards before I sent them, so I can make sure these are working. Other people ordered them on JSC and they accidentally flipped or rotated apart, and so the board didn't work, which is kind of a bummer, because desoldering the TUSS4470 is kind of a pain. This is the custom hardware with the STM32, but this is not like the community stuff. This is more like research stuff for the project itself. But this is also the board that is used in the dive sonar. I have a little higher drive voltage because I'm using a transformer. But to be honest, this is not like working as I expected. So like the Arduino hardware is actually the hardware I would recommend to get if you want to start with ultrasonics. Yes. I tested with a lot of transducers, like this 40 kilohertz for air, 1000 kilohertz for water mostly. Also with underwater transducers, like this 150 kilohertz NASA / Seafahrer echo sounder from the 1970s. Which is quite funny because you can use like this very old hardware and attach like this modern electronics and software to it and get like very high detail pictures, like for example with the fish. I think nobody in the team who built like these Seafahrer devices or Seafahrer echo sounders thought that you will ever get like these kind of pictures from there on a small shield that is like the size of your hand, which is quite funny, I think. And even with the lower frequencies or relatively low frequencies like the 150 kilohertz, you can already see like lots of detail here, like in the fish for example, but also lots of seagrass and everything. These small dots are, by the way, some electronic noise from the actual echo sounder that is on the boat. So while I tested with the transducer connected to my board, I still had the echo sounder running, and all these dots are basically measurements from the echo sounder itself. So it basically introduced some electrical noise into the lines on my board, which is kind of annoying, but not too bad, I would say. Also on the GitHub, on the Discord community, someone is currently building a version where they use the Arduino R4, which has Wi-Fi on board, and you can basically plug into this Wi-Fi via other devices or other Raspberry Pi or your phone or whatever, and you can see it on a web interface, which is very cool. I also planned this for the Python interface, but haven't done it yet. So currently you can only see like the raw data display, an interpreted number from the depth. Also you can, the settings change, like the sound speed, for example, like a default is speed in water, but in this case we're using the 40 kilohertz in air, so we can change that. You can also see like the interpreted or the detected depth, which is directly detected on the Arduino shield. So we can show this number here. And we can also use this number and send it via TCP to other software. For example, if I go to OpenCPN, which is a chart plotting software for open source C charts. It's a little bit slow and a little bit buggy sometimes, but you can see here depth is like dash dash dash, so no depth detected. And if I hit apply on the Python interface, you can see this number on the bottom left is transmitted to the OpenCPN software. Also works with iBoating. Not sure if I can. Let's see, what was it? I think yes. Maybe not. Maybe you can. Maybe we have to restart this here, and then again enable it. Yeah, socket error. Start NVA. Yes. Yes, now we have the depth that is detected on the top in iBoating as well. Also works on your phone. If you have iBoating on your phone, you can, and you're on the same Wi-Fi as the Python software, you can also send this data to your phone or other devices if you like. I'm also planning on sending the raw data. For example, on my ROV project, I need this raw data on other machines, so sending it via a Wi-Fi connection would be very cool. Currently, it just sends, it can only send the DVT or NMEA 183 standard DVT value, but not the raw data. But later I will also add that as well. Yeah, this currently this line is bouncing around like a lot. This is because this is in air and less of an optimal medium for ultrasound. So in water, everything is much clearer. You have less noise. So the signals in water look like very clean if you compare it to air. Also depends on the frequency, of course, but this is way cleaner than here. Yeah, as you can see. Also, like the depth detection only works on the TOSS 4470 chip, which is basically a threshold detection, which is not like optimal. But for the basic stuff and in water, it works quite well. We could also add like some averaging later, but yeah, this is not super needed. You can also install the Arduino alternative firmware, which is not like the one I have running right now, but this is the one firmware, and there's another firmware with NMEA DVT out, which only returns an NMEA 183 compatible sentence via USB or via UART. So you can connect, for example, a Pixar controller directly to your Arduino Shield or to the Arduino setup, or you can just connect the Arduino via USB to your computer and use the USB data source in iBoating or OpenCPN, which is convenient if you don't really care about like the raw data, or if you don't have another display and only want to use like the chart plotter software on your computer on your boat and want to know the actual depth below you. So this could be also a good use case for many people. In the community, like most people use it for boats actually, but a lot of people are using it like for testing, some for robots and underwater robotics, but like the vast majority or the largest group is basically the sailors who want to retrofit their boats. So yeah, the software is running on Mac, Linux and Windows, which is very cool, I think, because it's Python. Did I mention the dive sonar? So I also built a dive sonar based on the same hardware, or basically this is an STM32 based hardware with the TOSS 4470, which is like a specialized form of this. And this outputs the raw data to a Raspberry Pi and a 7-inch display and in a waterproof case. And I can take this with me diving and I can see underwater obstacles, for example, an anchor chain or a shipwreck or the ladder that is sticking in the water, or large concrete like weight for a buoy or something. Yeah, this was just like a fun side project, but not like really part of the whole open source project. But shows like the capabilities of the electronics. Yes, what else? This project was shown at the Waterkant Festival and Waterkant exhibition here in Kiel. Also on Science Day last Friday at the Makerspace, where I got some of these parts made. And also at Maker Fair 2025 in Hanover, which is a few weeks ago already. but that was very cool as well. So had a lot of great talks with people who are interested in the project and had some crazy and funny use cases for this. So yeah, it was a very cool event as well. Yeah, the spots are already in the hands of about 50 people, at least 50 people around the world in around 15 to 17 countries. Has more than 200 stars on GitHub. The Discord channel has about 300 members right now, and this is very cool. So since January, the project basically skyrocketed and was probably my fastest growing open source project, which is, I'd say, very cool, because this also shows that open source ultrasonic stuff is actually a thing, and that basically the market didn't have anything available there. So I'd say this is kind of cool, very, very fun to work with all of these smart people in the Discord community. Like we have like daily new messages when people work on this. We are building or thinking about building transducers. For example, this is all-in-one transducer I built a few months ago. Also how to watertightly seal stuff. Also, for example, building like the 40 kilohertz transducer, putting it in water, side scan transducer, like lots of stuff. People work on this. This is the web interface, which is very cool. Yeah, these are the very cool transducers we can compare them to. Yes, and also I just ordered a full batch of new boards so I can distribute them in the community. And if you like to get your hands on one of those, you can either buy them via the JIC, PCB ordering process, but you can also buy them directly from me. You can also buy them directly from me via openechoes@gmail.com or via the Discord community server. Every board is currently 50 euros a piece, including a small bag of goodies where we have the MP36 boost converter, a few cables, connectors, and everything you need to get started, except the Arduino and the transducer. But the transducers you can get for 2 euros on AliExpress, or you can, or if you have one lying around or have one attached in your boat, you can also use these as well. Yeah, I think that's actually it. So I'm very happy to have like this very large community around this already. And I'm, as I said, currently building like still new features for the software, building new hardware, building maybe my own transducers, building more electronics and everything. So if you have any ideas what to use it for and what to improve and what to keep and what to get rid of or whatever, feel free to leave a like, a comment, a subscription, a GitHub star, a Discord community join, or whatever you like. Feel free to comment, and I would like to hear feedback on this project. And see you in the next one. Thank you. Goodbye.